can I ask you about gravity? Because I'm new to this subject, and I've studied the sort of standard model a bit to the limit of my intelligence, which isn't very much. But I don't understand why gravity is never featured in any of these discussions.
Right. First of all, if you read my book, I think you'll realise you don't have to be that. You don't have to be that intelligent to do particle physics, actually. But the gravity is not in there for two reasons. One, because it's very, very weak. So the only reason we notice it, it's paradoxical, really, because it's the most obvious force, because it makes things fall. You know? But that's because there's no negative gravitational charge. So if you're near a big chunk of mass, then it all adds up, and in the end, it's a big force. But on the scale of tiny little particles, it's huge, orders and orders of magnitude weaker than anything else. So you can completely ignore gravity in terms of understanding the collisions at the Large Hadron Collider. It really doesn't make any difference. So that's one answer. You can do a lot without. The other is it's really hard. General relativity is a theory of gravity. It's not a quantum theory. It's, in fact, if you look at the way we put quantum field theories together, which you need in order to describe particle physics and even atomic physics, so they're not esoteric in that sense, they're obviously there. Then they all play out on the background of a smooth geometrical space-time. Now, in deference to Einstein and relativity, it's curved space-time, and you've got things like time dilation and stuff going on. Nevertheless, it's classical space-time, and there's no fluctuations in it. It's continuous. Nothing in quantum mechanics is continuous. It's all broken into quanta, and we have no theory of how to do that. And so the two reasons are, one, you don't need it, and two, it's really hard. Doesn't mean we don't want to do it, but